So a truck is moving up on an inclined surface uphill with some constant acceleration, and inside the truck there is this hanging mass on the ceiling of the truck. The hanging mass with mass m is deflected in such a way that it has an angle theta with the perpendicular to the ceiling. So the question is, what is the acceleration of the uh, truck, in terms of these angles, theta and phi? Okay, phi is the angle of the uphill, and theta is the angle of the deflection of the hanging mass from the ceiling. So, in order to solve this, we are going to first set up our coordinate system in such a way that this is y and this is x, and x-axis is going to be just parallel to the uphill. So we are going to try to solve this problem on imposing the Newton's second law on the motion of this hanging mass. So let's have a look at that. These angles, if there is a connection between them, or how can we express these and how can we incorporate these angles into equations calculating the acceleration A. The first thing is that the determine the forces acting on this hanging mass. The one is the gravitational force, which is just down, mg, okay, and the other is the tension of the string that hangs the mass m on the ceiling of the cart, which is T. These are the only two forces acting on mass m. And I will just draw some auxiliary lines. One line which is just parallel to this dashed line, which is perpendicular to the ceiling of the truck. Let me draw this line on the crossing the mass m. Okay. And this line is, let's extend this line so that this line is crossing the uphill by 90 degrees. And if you just extend this mg force line like this, what we get is we have a just tire over here, but I'm just going to get rid of this tire because I have to I want to show these angle relations. So this is the extension of the line of the gravitational force, and this line is just parallel to the line of this dashed line, which is perpendicular to the ceiling. So these angles are like these triangles, this triangle, and this triangle are similar triangles because this angle and this angle are inverse angles. They are equal to each other. And the other angle, which is perpendicular, the other angle perpendicular over here, that makes this angle to be phi. I hope you can easily see this from the similarity of these two right triangles, this angle and this angle. Why I'm doing this? Because we need to use these angles to just calculate the component of the forces acting on mass m in the horizontal direction. Let's draw also the horizontal direction, horizontal to the uphill. Okay, so since now the mass m is moving along this line just parallel to the uphill, along the x direction by our choice of coordinate system, so is moving along this line with constant acceleration a, we can write down the second law along this line. So all forces acting on mass m along this line must be just equal to m times a. A is the acceleration of the track, but since the hanging mass is just moving with this same track, just attached to it, keeping this angle just fixed. By the way, this angle theta and this angle phi are not necessarily equal to each other. What happens when they are equal to each other, I will discuss at the end of the solution. But in the problem, they are just given as different angles. So let's write down this equation, on the left hand side we have to put all forces acting on hanging mass along this line. I'm taking this direction to be positive, up direction as positive, and this direction as negative. And the first thing is that mg is have a projection on this line, which is mg times sine theta, but since downhill it is minus mg sine phi. This is angle phi. It's minus because the component is pulling the mass in this direction, which is down with respect to this x-axis down. And the other force is this tension component on the x-axis on this line. And since this angle is theta, the component of tension T on this angle is just nothing but T times sine theta. But it's plus because it's pulling up in this direction. Plus T times sine theta. And that makes this part equal to m times a. So we have to find a in terms of probably mass m and g and sine of the angles theta and phi. But one thing is that we have to replace this t because this t is unknown, okay? But we can find this t in terms of mg. How? Well, if you look at this again, the mass m, by the choice of this coordinate system, the mass m is not moving in the y direction. So it's not moving in this direction. Not moving in this direction makes sum of all forces acting on mass m in this direction to be equal to 0. So just think of this direction. Well, all forces acting on this direction is going to be equal to 0 because there is no any motion in this direction. But in the upward direction, t times cosine theta, there is this t times cosine theta. In the downward direction, there is mg times minus mg times cosine phi. I hope, again, you can easily see this. And this makes this sum must be equal to 0. And that makes t in terms of mg to be cosine phi divided by cosine theta. So when you put this t expression over here, you get minus mg sine phi plus mg sine theta divided by cosine theta makes tangent theta multiplied by cosine phi equal to m times a. So from this we can just cancel all m's on every term in this equation. That makes a to be equal to g times, right, g times tangent theta multiplied by cosine phi minus sine phi. So this is the expression for the acceleration of both track and the mass in terms of g and angles theta and phi. Okay, so this is it. This was the question. I mean, how do you express the acceleration A in terms of these angles, and possibly, of course, there is gravity, which is downward. And the other thing is, let's make a comment on this. If the track were moving like at a constant velocity uphill, then A will be 0, but that makes hanging mass to be just perpendicular to the ground. Hanging this mass perpendicular to the ground makes theta and phi to be equal to 0. You can easily just check this by use of trigonometry. So if you put theta and phi is equal to each other in this expression, you will just find A to be 0. So that just verifies this expression is correct. If you put just theta is equal to phi, and theta is equal to phi, this is sine phi divided by cosine phi multiplied by cosine phi makes this sine phi, and there's also sine phi over there. Sine phi minus sine phi makes acceleration to be 0. In that case, which is the case, if the track is moving up with a constant acceleration, the hanging mass is going to be hanged just perpendicular to the ground, and that makes theta equal to phi.